So that's our dynamic model. And then we're going to compare this to a static, and we're going to use the DC OPF. So the difference here is that that runs a power flow, and then if it sees that a line is overloaded, it collects up all the overloaded lines, just trips them all off. It will then redispatch the generators according to the new topology. It allows some variation in some of those generation and loads. It allows them to move a little bit, essentially to emulate the behavior that you would get from some kind of frequency response. And it includes over frequency generation tripping. So essentially, if I have an island where there's too much generation, it will then start disconnecting the generators from starting from like the smallest one in order to try and find a kind of a static operating point that converges. So we've got some kind of emulation of some of those dynamic processes within this, but it's obviously not running the actual dynamics itself. So those are our two different models. And then to trigger any kind of outage, we're using n-2 contingencies. So these systems are safe for n-1. They're fine, like secure for an n-1 situation. So we need to hit them with an n-2, something more significant, in order to cause a problem large enough to start a cascade. And most n-2s don't. Most n-2s are fine. It's only some of them that actually cause problems. That's actually a really interesting question is, how do you find out which of the initial contingencies you need to cause to cause a cascade in your system? It's not a trivial question to know where the kind of combinations of multiple outages will be that lead to a big cascade in the system. So we need to figure that out as well.